Hello, this is Jonathan Temple, and this is a lecture about the estimation of general linear models using least squares, and then what happens if we do least other things. This is a lecture in the course Fundamentals of Multivariate Modeling or Educational Psychology 905, and this is the 5th online lecture we have. So today we're going to have an introduction to estimation. You could go ahead and use the hashtag WTFTemplin if you'd like. I don't know where you're going to put the hashtag though. So if you're live tweeting a video that's on YouTube, that's awesome. Put it in the comments maybe that'd work. Why we're talking about estimation? Well, I'm going to go into that. Why we do it, why it's important. But the bottom line is. How do you trust the numbers that come out of the computer, and why should you? We're going to go over a little bit of least squares estimation for our linear models, and we're going to take this opportunity to introduce other types of linear models that use a different type of least in what we do. So we're going to talk about quantile or median regression. So why is estimation important? Well, often in these types of statistics classes, you don't see a lot of estimation discussed very frequently. It's typically very technical, often very intimidating. In fact, and as an instructor, it's intimidating to think about trying to describe something to you that I'm only halfway knowledgeable about anyway. But really, the reality of it is that estimation is critical in what we do. It's of critical importance because the quality and validity of the estimates that come out of the computer and the inferences or the decisions we make about our hypotheses depend on how the estimates were obtained. And not only that, in the recent, in the last 25, 30 years, we've had new methods appear to estimate models and obtain parameter estimates. And quickly they become used in widespread areas without anybody asking whether or not they're any good, which is really a problem if you think about, do you believe the numbers that come out of the computer? So let's imagine this absurd example is why I'm telling you about this. Let's imagine you're trying to estimate the mean IQ from some type of intelligence test. And let's imagine, typically in R or SPSS or whatever you use, you have your data there, you push a few buttons, you type a few things, hit enter or return, and next thing you know, you get a number, right? So this black box behind it. So R is less of a black box. You actually see the code behind it. It's open source. Apart from that aside, let's imagine instead of that black box, you call me up and you say, hey, Templin, what's the mean IQ? And similar to the black box of SPSS or R, I say, I know exactly what it is. It's 20. And you'd be like, wait a minute. Do you need to see my data? I'm like, no. The mean of your data is 20. I know it. That's what it is. Would you believe me? Yeah. Would you go into your paper or into your study or into your dissertation and say, yeah, means 20. I used Templin. There you go. Have a nice day. It's kind of absurd, right? You would never do that. But typically, that's what's happening. I mean, you're putting your trust in a computer system of what's happening in the black box, but really what we need is an estimator that has a basis in reality, and particular that's been studied statistically. There's theory about how estimators work, and there's knowledge about what happens when we use certain estimators, and we want to be able to have an estimator that works in that way to give us the numbers, so we can believe the numbers when they come out of the computer. So that's the most important part about it. Here's how estimation works. And what do I mean by estimation? Estimation is the process by which you take data and a model and you transform that into results. So in a linear model sense, pretty much we've only seen linear models up to this point in the semester. The sense of estimation is that you have a data set, you form a model, you say this outcome is predicted by these predictors, you put that in a LM function in R usually. You hit return, and then you take the summary of it, and sure enough, there's numbers there. How did it come about to get those numbers? Well, here are some of the methods that we use. Most of the estimation we do in statistics come from three different types of routines. We minimize something, we maximize something, or we use simulation to sample from something. And so what I mean by something, these are functions of our data based on our model. So let's talk about minimize. That's today, what we're talking about today. Typically, we find the word minimize as in, we know it's a minimization process because we want the word least to appear. Typically, we hear things like generalized least squares, ordinary least squares, which seems very plain, weighted least squares, diagonally weighted least squares. One of my other favorites, weighted least squares, mean and variance transformation, although T didn't make it on there for whatever reason. And then finally, iteratively reweighted least squares, which actually probably would be my favorite for the least, the minimized. But typically, when we do estimation, this one becomes the estimator of last resort for whatever reason. Generally speaking, particularly in multivariate models, our gold standards are something other than least squares. And that's because least squares provides only an approximation to really what we do in a multivariate sense. Although, in a univariate sense, when we have one outcome in a typical linear model, these work just fine. So that's where we're at. Now on to the maximize something. Typically, we'll hear about estimators that have the word maximum in their title. You might have maximum likelihood, or ML. We might have residual maximum likelihood, or REML. You might have robust maximum likelihood. And oftentimes you'll hear things like full information maximum likelihood, or FIML. Gosh, it's terrible. But typically, this is the gold standard of estimators. And in the next lecture, we're going to see why that happens to be. Although I will say that the world is changing a little bit now, and as the more complicated we get with our statistics and our models, that's changing away a little bit from maximum likelihood and toward the last example, which is the use of simulation to sample from something. And so this is a much more recent advance in statistics, but we typically use some type of resampling technique, often involved in Bayesian statistics. One of the things that you'll see to hear this is something about Markov chain Monte Carlo, or perhaps Gibbs sampling, maybe even Metropolis Hastings, or Metropolis algorithm, Monte Carlo. I'll go a step further. There's new ones called Hamiltonian Monte Carlo or hybrid Monte Carlo, and there's all sorts of other things, but typically you'll see some type of Monte Carlo as in a sampling or stochastic or random process that brings about the parameters. So unlike parts 1 and 2, where we have this big function that we're trying to minimize with respect to or maximize with respect to the parameters of our model, in simulation it's a little bit more brute force. We're essentially sketching the distribution of the parameter that it comes from based on these types of methods. So apart from Bayesian, you may also see the sampling part in bootstrapping, combinatorics. And so typically this last one, bootstrapping, gets used when we're not even sure about the distributions we're talking about. But then Bayesian methods get used when either the assumptions that underlie 1 or 2 fail, or perhaps when our model is so complex that it would take number 1 or number 2 excessively long to estimate. And I'm not talking like how we do things in R and we get least squares estimates within seconds or fractions of a second. I'm talking about estimation that takes a week or 2 weeks or even a month. And believe me, I've been there before. So let's get into estimation of linear models or general linear models using least squares. So let's recall our general linear model. We have y, our outcome. It's predicted by a function of beta or x and z. So here we have an intercept, main effect of x, simple main effect of x, simple main effect of z, interaction between x and z. This is also called the model for the means. We also have the model for the variances where E shows up. And dating to about 1840, these linear models, general linear models, have been estimated with a process called least squares. And what do we mean by that? What we're going to do is we're going to try to find the betas that we have, the fixed effects, that minimize the sum of the squared error terms. Right? The error for a person was equal to y, the observation of the person, minus the predicted value of y. So we want to minimize that. So once we pick a beta 1, a beta 2, a beta 3, we can form y hat, which is the predicted value for a person. And once we form y hat, then we can go take the difference of it with the observed value, square it, and we get e squared for a person. So because the basics of estimation are critical to understanding the validity of the numbers you're going to use to make inference from, we're going to detail that process. Another reason why I want to do this is to get you to think about there's multiple ways to estimate certain types of models, each of which have a positive part to it. So right now we're going to start with least squares, and we're going to end with maximum likelihood in the beginning part of this semester, and then we're going to go later into the sampling methods as we get further along. The least squares estimation that we're going to talk about today is to get you to visualize functions that we use that are functions of these statistical parameters, in our case the betas that we talk about. And it's a function of the betas and the data that you have to figure out where you would pick the estimates. And so what I need to talk about with this is an oversimplification of the process. In practice, least squares estimation for these linear models does not exactly do this. For general linear models with conditionally normal outcomes, we have what we call a closed form solutions, in that there's one equation that we have that's a function of our data that provides an estimate of our fixed effects. So it gives us the least squares. It's found through calculus and algebra. And in other generalized linear models that use different types of distributions other than conditionally normal, a similar process is held, although it's not usually a closed form. It's an iterative process. It's iteratively reweightedly squares. So in the end, I'd like for you to understand that not all estimators are created equally, and that some can be trusted more than others. And furthermore, I'd like for you to understand how this process works so you know a little bit more about when you can fix things when they go awry. So diving right in, let's go to least squares estimation. Least squares works through minimizing the squared error, but what goes into that error drives the process. So again, error is our observed variable minus our predicted value for each person, which really, with the predicted value, we could substitute in for our model for the means, right? Y minus that. So if you were to do this, and you probably wouldn't, this process would look like this. We pick some initial values for the regression slope, right? So let's pick values of beta 0, beta 1, beta 2, beta 3. Pick them at random. Make them all 0. Do whatever you like. It doesn't actually matter because the process that we outline here will work for the same way. So once we pick those values, we calculate y hat using this formula at the top. And then we calculate error based on that y hat. Right? We work backwards over to error. Then we take the sum of the squared errors, and that becomes what we call our objective function. That is a function that we use, mathematical term for a function that we use that we're trying to find the minimum of in this case. And then what we do is we repeat values 1 through 3 until we find values of the regression slopes that lead to the smallest value of the objective function. So, for example, we're going to have a data example here with 5 observations, just to make it a little bit more simple. And the observations have 5 IQ scores and 5 values of job performance. So let's imagine you're an employer. You have a bunch of data on employees you've hired. You have an IQ estimate of their some type of IQ test, intelligence test, if you want to call it that, and some set of observations that refer to how well they performed on the job historically. The descriptive statistics that we have here, we have the mean IQ from your sample is 114.4 with a standard deviation of 2.3, and the mean performance of 12.8 with a standard deviation of 2.28. And here, of course, is a covariance matrix that you can see between those. And here's our data. All right, if I center IQ, let's imagine I'm going to use IQ to predict performance, and let's center IQ by its mean. Right, so this 0 point is mean centered. This really reflects an IQ of 114.4. Right, so this is IQ minus 114.4. Now you've got 5 points, and sure enough, that thing looks like IQ is related to job performance. I wonder what type of job that could be. Think about that one over. Anyway, You don't want to see my calendar. Moving forward, what we want to do is try to pick the values. In this case, there's two parameters, beta 0 and beta 1. Let's pick values of those parameters that try to minimize the line. So I'm going to switch over to our R example here. And sure enough, in this section of code, we can evaluate what the mean and what the intercept and what the slope might be. So let's imagine I'm going to start with a value of an intercept of 13, the value of slope of 1, and sure enough, this is what's going to happen. If I comment out what the actual values happen to be here, let's take a look at how my guess of 13 and 1 works with these data. Here you go, my sum of squares error. All right, the sum of squared errors. This line looks pretty good. 13 and 1 kind of goes right through the dots. Sum of squares error of 276.96. Great. Let's see if we could do a little bit better. What if I did 13 and 2? Should we try that out? Again, what this does is it forms predicted values, and then it goes and forms the sum of squares error, and so forth. 13 and 2 has a higher sum of squares error. Uh-oh, it's a lot different from the line, 517.04. All right, so 1 was closer. Let's try again. How about 1.2? Let's see if that gets any better, shall we? All right, one more try. Sure enough, it did do better than 5, or sorry, a value of 2 for beta 1, but really sums of squares error here, 316 didn't beat a value of 1. So that's a process that you can think about. We're just trying to find values of beta 0 and beta 1 that minimize the squared errors that we have. And actually, I can tell you what those values are because I can just do the linear model. And here we have the actual linear model has an intercept of 11.5915 and a slope of negative. No, it doesn't seem to work right there. Let's take a look here. Yeah, that doesn't seem to work. What did I do wrong? Oh, I know. Didn't reset my IQ variable. Let's do this. There we go. When I put the actual values in, you see that the estimated values of 12.8 for the intercept and 0.96 for the slope lead to a sum of squared error of 1.169. And again, if I tried my 13 and my 1.2, what you'll end up seeing is that value of sum of squared error is actually higher than that. So it turns out, through the wonders of calculus and math, you cannot actually do any better than the output that you're going to see right here with those two estimates. And that's because these are the values of beta 0 and beta 1 that minimize the sum of squared error based on calculus. They're the ones that work the best. So there's nothing you can pick that would work better. So now, go over here to my slides. Let's take a look at what this objective function looks like, right? So let's imagine this beta 0 right here and beta 1 right over here. This surface that you see, this graph with this curve that you can find in the next section of R, describes for any given value of intercept, beta 0, and slope, beta 1, like where this dot is, the part of the surface that's up above it is this value of sums of squares error. And so this surface, as it starts to get down, somewhere down under here is the value that minimizes, the value of beta 0 and beta 1 that minimizes the sum of squared errors. So on the left here you have the surface plot. On the right is taking this surface plot and then drawing it using contours. The contour map is like what you'd see in camping or in hiking or describing elevation of a surface of like mountains, where the lines represent equal values in camping. This would be equal elevation, or in mountains equal elevation. For us, this is equal values of sum of squares error. Right? And sure enough, right here, if we look at where the actual values happen to be, 12.8 was the lowest value, or the value that minimized 12.8 and 0.96. So here's 12.8, 0.96 is right about here. And sure enough, if you go into the middle here, That's where the minimum happens to be. That's the minimum of the function. So you can visualize what's happening. What we're trying to do, what the computer is trying to do is pick beta zeros and beta ones that minimize this function to give us results. And basically we're saying the results we'll find is that the line that we have goes straight through the points. It has the minimum amount of error that we see. So that process of least squares estimation in general linear models does not need an iterative search. In fact, we can do calculus. I'm not going to, but let's just talk through the process of calculus to understand where this is going. Once you have an objective function, right? Once you have this function right here, that's our objective function, and we substitute into it, put it in with respect to the parameters we're trying to use to minimize the process, then we can use calculus to figure out the values of the parameters that give us the minimum of that objective function. And sure enough, there's a term in calculus called a derivative, which is a slope of a tangent line. A tangent line, if you have a curve or something like this, a tangent line is a line that just barely touches a curve at the one point and talks about direction. And sure enough, in the surface, if you put a tangent line where that slope is 0, is the value of the first derivative. And we find the first derivative, set it equal to 0, solve for the parameters, and sure enough that, well, we technically don't know if it's a minimum or a maximum, but we can figure out what that happens to be. So sure enough, we can use calculus to figure this out, and what we end up seeing is you can come up with a slope based on a linear predictor, or if you really love matrices, which we haven't gotten matrix algebra yet, but we will in a few weeks, there's one equation that rules them all. It's this x transpose x inverse x transpose y. If you learn that one, you learn that x is your data, your predictor data, y is your outcome data. You put that into this function, and you get all of the betas all at once with one line. So it's pretty amazing how it works, if you like math. So the ramifications are, though, because we have this one equation, we have what's called a closed form, meaning that we can go and get direct estimates of our parameters. They will work nearly every time. The only time it starts to fail is you'll see there's this x transpose x raised to the -1 power that's an inverse. When we get to the matrix algebra portion of the course, you're going to learn that the inverse matrix, sometimes inverse matrices don't exist. You can think of it as like dividing by 0. And the times when these inverses don't exist is when you have perfect collinearity or multicollinearity. You may have heard that term before. It's usually thrown out there by reviewers who are looking for something to criticize a paper on that don't really understand it. But collinearity is only a problem when this thing can't be inverted. And when that happens, you typically see things like estimates of standard errors that involve like 300 million or some odd number. It just becomes terrible. So we don't really need to worry about it too often. So most of the time, this will work. But that being said, this is the simplest case of what you will do in pretty much any model in your life. Virtually all other estimators you encounter do not have a closed form. So even least squares estimators for data that are not continuous, that are not conditionally normal. So without that closed form, what we do is that sort of a process of searching the objective function for its minimum, and that search that we go on is iterative. Like there are certain iterations. So we take a guess, we check for the minimum. We go a step forward. Now that guess we take is going to be educated. There's a process using calculus that helps us figure out exactly what the next best guess would be. But again, we have to go take a step forward, see if we got the minimum. How do we know it's the minimum? Well, we know, again, the tangent line at that value, the slope of it should be 0, so we can calculate what that happens to be to figure out if we're at the minimum. You can think of it this way. It's kind of like finding the drain of a pool. If you go swimming, at the bottom of a pool, there's usually a drain of some sort. If you close your eyes and you hold your breath long enough, if you're trying to find where the drain is, you sort of have to put your hands down at the bottom of the pool, and you can sense the slope itself. And we're going to use that sense of slope to figure out where the minimum is. So, backing up here, if I told you before that maximum likelihood is sort of our gold standard estimator right now, why on earth are we using least squares still? Well, sure enough, They are easy to compute. They will pretty much always give you an answer. And we can show that they're equivalent to the maximum likelihood estimates that we find if we use a linear model. So more often than not, when we have this simple linear model, when we have this like conditionally normal data in a general linear model, we know that least squares is equivalent to maximum likelihood. And in the next lecture, we're going to talk about why maximum likelihood is so good. So we end up understanding that the process we're doing here turns out to be that maximum likelihood is all the properties are still applied because we are actually equivalent in this case. So we're just going to now know that maximum likelihood estimates have some really good properties that allow you to believe the numbers that come out of the computer. And why we use least squares in this case is because they're shown to be equal to maximum likelihood estimates. So that therefore we get those same good properties. Now, least squares sometimes fail, particularly if you have data that aren't continuous, or if you have multivariate models with continuous data, particularly when you get repeated measures or longitudinal data. You'll find that the least squares estimates are limited at best, but frequently don't even work. Part of the reason is if you have missing data at all, they don't know what to do. They sort of and they just kind of blow up, or they give you numbers, but the numbers aren't believable that much. The other problem is that they're very limited in figuring out what the covariance structure is between observations, and that's going to be an increasingly important part of what we do in statistics, at least through multivariate models we get to. So least squares is great for one outcome because it mirrors what we get with maximum likelihood, so therefore it has great properties, but it doesn't always have great properties with what we do, and so that's sort of a problem as we go forward. All right, there are other types of estimators out there, and one of those types, they start to fall into the category of robust statistics or robust general linear models. And so when I hear the word robust, I think of in English. What do you think of when you hear the word robust? For whatever reason, I'm thinking coffee right now. Robust coffee is something that's, you know, strong or thick. I don't know. Same thing works with robust estimators. And sure enough, we're going to see that there's another minimization process that we use to find these. So let's imagine this. This is just more to expand your horizons a little bit and get you thinking outside the box about what we can do with numbers. Let's imagine if we change our objective function, right? So this is our objective function, least squares. We're minimizing, we're finding the minimum of the sum of squared error terms over the case of our parameters. What if we change that minimum from a square to an absolute value? That'd be a little bit different, right? So let me go back up a little bit. The purpose of squared error. The reason why we have to square error is if we take the sum of error across all of our people, the sum of just the error term turns out to be 0. Right? And that's partially because we said error follows a normal distribution with a 0 mean and some variance to it. So to get a 0 mean, you need the sum of the values to be 0 because the mean is the sum of E over N. So we can't minimize the sum of E because it's always 0. We have to do something to it, and so typically, or at least at the beginning with, we squared it. Another thing we could do is take the least absolute value, or the least absolute residual. Right? Let's take an absolute value. Absolute value, again, if you have a -1, the absolute value of that is equal to 1, right? It turns everything negative into positive. So minimizing absolute values actually changes several properties of the estimates. Oftentimes it's called median regression, or more generally quantile regression, where the median is at the quantile point 5, which is sort of the middle point of a distribution. The estimator itself is often called an L1 or robust estimator, as opposed to in least squares we have an L2 estimator. Sure enough, the L2 estimator is not robust. So you can think of this as like the hazelnut roast coffee, right? Whereas this thing is like the dark roast right here. coffee examples don't go very far. The regression line, sure enough, in the L2 estimator, the regression line used to go through the mean, but now when we use the L1 or robust estimator, it actually goes to the median of X and Y. And so you think about what happens when you have a skewed, let's imagine you have one variable and it's skewed. What happens to the mean versus the median? Well, the mean gets pulled out by the tail of the skewness, much more so than the median does. And the median is thought to be a little bit more robust to the influence of outliers on data. And the same thing works with regression when we use the least absolute residual. And so now it's robust to the aversions of outliers that might come and bias the regression line itself or the parameters of the regression. I'll show you that in just a moment. More generally, the loss function or the objective function can be defined as a process of minimizing the least absolute residual subject to some weight, tau, where tau is the quantile you're at. So you have tau times that plus 1 minus tau times, for every time y is greater than the predicted value, and then when y is less than the predicted value of 1 minus tau times this. Basically what this is saying is we don't just have to be at the median at 0.5, we can pick a different value, a different quantile, like the 25th quantile or the 75th. It's like a percentile, right? This is a different part of the distribution and do regression through it. And that really changes the story you can talk about with data. I'll see that in just a bit. So, you don't want quantile regression in SAS, but here it is. Here is, actually, you know what? I'm going to show you this example with SAS, but it works the same in R, and I have the R code for it right over here in our example file, right here. So, in SAS, there's a proc called proc quant reg. In R, there's a package. The package is called, sure enough, quant reg. Hooray. The person who developed this is a person by the name of Roger Conker, who I worked with at Illinois, and this is a fantastic package. It's used a lot in economics of all places. So what happens? Here are two different estimates that we get. The black line here is the estimates from least squares. The dotted line is the estimates from the median or L1 estimates. This is L2 right here. See? And so they're not that different with the same data, right? Here's the intercept. So for the quant reg itself, and actually let me just go, you can't see that. Let's go over here. Let's imagine we are looking at the L1 estimates right here. So here's our RQ is the function we use. And we look at the summary, and sure enough, the intercept, with scientific notation, is 12.4. And compare that to 12.8 that it was before in our analysis. And in the slope was a value of 1, although the solution may not be unique, which is one of the problems that we have here. And sure enough, that's a value versus a slope of 0.96. And if I were to plot them on top of each other, here's where you'd see the plot. They're really close to the same values. Now, here's the objective function of that quantile regression. And sure enough, take a look at the shape of this thing. It is no longer what we'd call a smooth function. There are these little well-defined points that evaluate here with it. And that's where the problem starts to lie, because sure enough, we can't usually do the same type of calculus. The derivative can't be defined here. So how we actually find the minimum of this is a little bit different than what we do if we were doing an iterative search over the L2 estimator. But, so the process gets a little bit more complicated. But then furthermore, it's a little bit harder to get the estimates. The properties of the slopes aren't as well known. We may have to use resampling or bootstrapping to get standard errors, and so you'll get different results. This is a little bit more complicated, a little bit more difficult. You're not necessarily guaranteed that the results are good. But let's take a look at what happens if we believe this. Let's imagine we add a sixth case right down here. All right, before we saw our regression line went right through these dots, what do you think is going to happen to it when we have a dot down at the bottom? This point is going to be said to leverage the regression line, and sure enough, it's going to look like this. All right, so here is what happens without the outlier. Our least squares estimates, the typical linear model, were 12.8 for an intercept and 0.96 for the slope. But with the outlier, sure enough, The intercept changes slightly, but look at the slope. It goes to negative 0.63. On the other hand, take a look at the quantile regression estimates. 12.4 and 1 and 12.4 and 1. They are the same. So if I go forward, here's a plot of them, right? The black line right here is our original least squares estimates. The dotted line down here is how they change with the influence of that one outlier. It's literally the word what we describe this with is leverage. This point leverages the entire line to come on down. But the dashed line here is the quantile regression, the L1, and it is not affected by that outlier. So one of the things that changes, if you change the estimator slightly, you get a little bit better properties or a little bit better results depending on the type of data if you can believe them. So you have a harder time believing the results. They're not as guaranteed to give you the good function, the properties that ML might give you, and they're certainly a lot harder to get than least squares. But if you do get them and you do believe them, then the result might be a little bit more robust to outliers that you see here. And we have a bunch of other examples. Sure enough, quantile regression is a useful research tool when your data might be skewed. So if you have like income or money of any sort, this is where it shows up in economics a lot. When you might have some possibly outlying observations present, or perhaps when you have some crazy interactions between your independent variables and the dependent variable. The quantile regression, though, cannot help with dependency between cases or with non-constant variance or residual terms. And what I'm going to show you here, an example, is in SAS using Quantreg, but the data are not public, so I can't go a little bit further into what's happening. But the package Quantreg and R would be similar, give you similar results. So this is just more kind of informational. You could do this if you wanted to. So here what we see is we're going to call this a study in change detection speed, right? So we're going to take an outcome, which is reaction time, the time it took to detect the change between two otherwise same pictures, right? So this is the average. So a person would come take this is sort of a boring task. You see two pictures and you figure out where the change is between the two, and you do this over and over and over again. And if you take about 60 trials, this is your average reaction time. The age of a person. This is a study that involved kind of elderly populations, and so these are a little bit older people. So the age in years centered at 65. And now we're going to have a measure of near vision. So the higher value here, it's centered at 20/20 vision, which is a value of logarithmic units. I'm not fully understanding what this means, but basically the higher this value gets, the worse vision a person has. So here our goal is to predict reaction time across all quantiles to see if age, near vision, or their interaction have an effect on reaction time. And the reason for this is that in the aging literature there is a debate about where slowing reaction time happens, whether it's a general shift or it's more spread out. So at first we're going to fit the least squares GLM linear model, and then we're going to try the quantile approach. So here's least squares, and here are our estimates, and we see that there is a non-significant interaction between age and vision. There is a significant simple main effect of age, but a non-significant simple main effect of near vision. Right, so that's where we'd start. But let's take a look at our plots. These are the residuals, and sure enough, there are a couple outliers. This is the distribution, the histogram of the residuals, and these guys are kind of making us think, wait a minute, we might have some influential observations in our data. What would happen if we were to do this with quantile regression? So what we're going to do is we're going to set a random number seed of 8675309, and you might not be old enough to remember that, but here you go. Here's a YouTube link if you'd like, and sure enough, this is what we get out of it. These are the quantiles ranging from close to 0 all the way to close to 1, and each of these plots is a picture of the parameter. The blue around here is the standard error of that parameter, estimated through resampling methods. And sure enough, the intercept we don't really talk about too much. But let's take a look at the interaction. The interaction, this 95% range, 0 happens to be right here, and we'll see that for most values of the distribution of reaction time, the interaction is not significant in that the range, kind of the range of the parameter, the range of the blue shape, includes the 0 point. There are a section, though, of quantiles where this interaction may be significant, and that's somewhere between the 0.2 and 0.4, so like the 20th percentile and the 40th percentile of the distribution of reaction time. That's where the interaction may be important. Similarly, we can take a look at vision and how much that impairs a person's ability for reaction time, and a similar story takes place in that here, where it's significant is very low, like at very low levels of reaction time, vision plays a role, and it kind of anywhere below 0.4, it's thought to do so, whereas the bulk of the distribution is not significant. And finally, age does play a role. In fact, the faster the reaction time, the lower the effective age, although it's still significant because 0 is right down here. And as you get a faster and faster, the slower reaction times, the higher quantiles, age is playing much more of a role in that. So age is causing, basically, if you look at this, you're saying the story is that age is really playing an impact in how fast the person happens to be. So moving to the next slide, that's basically telling you what all this happens. So the interaction changes depending on what we do. Let's take a look at 3 specific quantiles: the median, the 25th, and the 75th quantile. This is like the 25th percentile, the 75th percentile, and the 50th percentile. Here are the results of quantile 0.25. These are the fast people, 25th percentile of reaction time. Here's where we see significant interaction. That means we have to interpret this as the effect of near vision when a person is 65, which is nearly significant, but sure enough, as age increases, this effect gets more positive. So shortly after age 65, near vision starts playing a role. The person's ability to see, it really impacts reaction time. Similarly, age is significant when near vision is at 20/20, and the effect of age increases as a function of near vision getting worse. Now, for people in the middle group of the speededness, we see that the interaction is not really significant, meaning that, again, if we took this out of the model, this would be essentially a basically, when this is not significant, if we were to take it out, then near vision would be an unconditional main effect, but it's not significant either. And so what we're seeing is that really, if you're on the fast side of things, age matters and vision matters. But if you're sort of in the middle of the distribution, it's only age that really plays a role. And the same thing happens as you get toward the upper end of the reaction time. Age is playing a role, but not near vision or the interaction themselves. So a lot more rich results that you get out of this method. It's really interesting to see how it works. But quantile regression, you may have already seen results of this in different fields. So here's an example, a plot from the National Weather Service, or actually this is National Oceanic and Atmospheric Association. This was a plot from several years ago that talked about, this was the number of tornadoes up through that point in September. And these lines that you see here were the quantiles, although the top and bottom were the maximum and minimum. These are the actual values that you saw. The yellow line represent the 75th quantile, the 75th percentile, right? So this is like a quantile regression right there. There's the 50th percentile in green and the 25th in blue. So you see these plots from time to time. Where often you see this is also if you go, if you have children, or if you remember being a child and you would go to a doctor's office for a physical and they'd take your weight and height, they'd compare that with certain quantiles based on age, and those are also quantile regression plots as well. This is essentially the same type of information, but now for salaries, the 25th or the 75th percentile, the 50th, and the 25th. So Wrapping this up, it's a lecture that was just trying to get you to introduce you to estimation. Estimation is critically important for figuring out what you get from the statistics, whether they're worth believing, and changes in estimation can bring about radical changes in the results too. So it's pretty cool. I hope the quantile regression was just informational to you. You may even want to try it with if you're ever doing a linear model. It's kind of fun to try, and the QuantReg package is very easy to use. But just remember, not all estimators are created equal. So if you ever get presented with estimates from someone, ask how the numbers were attained. Talk about where that is, because that starts to talk to the quality of the estimates themselves. And if you're ever working on getting your own estimates, try to get the best you can with your data. Try to understand what the estimator happens to be. Now, what that happens to be will come from either maximum likelihood or Bayesian, and we're going to see why in the next lecture. So that's all for now. Thank you very much for watching.